Alrighty, my people. This is the third video for 3.10. And let's just go ahead and go over these first couple sort of conceptual pages in the beginning. We have already explored linear approximation, and we're going to take a peek at a related application, which is called differentials. Now, usually when we see dy dx, we think of it as a single quantity, but it's a ratio, okay? And that ratio is going to help us find the approximation of the change in a function instead of finding the approximation of the output of the function. And it's related, and I'll show you a visual representation here in just a second. But first of all, we need to remember that if y is equal to f of x, then dy dx is equal to f prime. Now, like I said before, we have thought of dy dx as a single quantity, but it is a ratio, and therefore it can be changed into dy is equal to f prime of x is equal to dx. And the dy and the dx are what are referred to as the differentials, okay? But what this means is it's not only the function values of the tangent line that approximate the original function, but getting back to why we had tangent lines to begin with, if the slope of the tangent line approximates the original function as well, that's going to give us an approximation of change over an interval. So as dx changes, we can actually calculate approximately how much y has changed. And so this will all make sense, a little more sense here in just a minute, okay? So that means that we can use differentials to approximate how much a function output changes based upon a change in input. And here's what I mean. Let's look at this particular schematic right here. And basically what we were doing when we were looking at linear approximation is we were looking at, finding this point to approximate this point, right? But what we're doing here instead, and of course it's related, is we are finding this distance to approximate this distance. And of course they're related. This right here is your dx. This right here is your dy. This right here is your delta y. Okay? And the difference is this. Our dy is going to be the approximate function value change, and the delta y is going to be the actual. Notice that in this picture right here, the delta y is the difference between the output from here to the output to here on the original function. Whereas this right here, this represents dy, not delta y, and it represents the change in output from over this delta x period, but it is using this tangent line and its approximate slope to the original function to actually represent that. So again, we're not looking at approximate outputs, but approximate change in outputs. And that's basically what the difference is between the last topic and this topic. So related, but distinct, okay? So what we need to do here is, of course, we need to run through an example or two. Now, let's say that we are given the function f of x is equal to x squared plus 2x, and we want to anchor that. Basically, our point of tangency is going to be at x is equal to 1. Now, of course, when x is equal to 1, the output is going to be 3, but actually in this case, we really don't need that, okay? We simply need to recognize the fact that if f prime is equal to 2x plus 2, what that means is we're going to think about it instead as dy dx as 2x plus 2, so that we can rework it as 2x plus 2 dx is equal to dy. And dx is going to be, of course, this dx. How far you have moved from 1. So if we move from 1 to 1.1, our change in x is 1/10. We want to use this tangent line slash differential sort of construct right here in order to approximate that particular output. Now what that means is, for our purposes here, dy is 2 times x plus 2 times that dx, and that's going to be 4 times 1/10, 4/10 or 2/5. Okay. Now I can compare this from what the actual outputs would be, right? So if this is dy, then my delta y is simply going to be 1 squared plus 2 times 1 minus 1.1 squared plus 2 times 1.1. Now, of course, this is going to give me a negative, right? So I basically can slap absolute value bars around that, but you don't have to, as long as you understand that the distance is always, of course, positive when we're dealing with something like this. All right, and so what we're going to do is this is going to be 1 squared plus 2, so 3 minus 1.1 squared plus 2.2, and we get negative 0.41. Of course, absolute value bar that because we're dealing with distance here. So basically, once we put the absolute value bars around here, this winds up being 0.41. Well, of course, this is 0.4, and that is a pretty close approximation for the change. So what that means is you've approximated that as we've moved on this function from x is equal to 1 to x is equal to 1.1, your output has changed approximately 0.4. Now it actually moved 0.41, but you have to admit that's a pretty close approximation. So we have determined not the approximate output, but the approximate change in output. And just to drive this home, we're going to do another couple examples. All right, let's look at this one. We are given the function f of x is equal to x to the negative 1, and of course that's just the reciprocal function. That's y is equal to 1 over x. So if I have y is equal to 1 over x, or of course I can rewrite it as x to the negative 1, then dy dx is equal to negative x to the negative 2, or negative 1 over x squared. That means that dy is equal to negative 1 over x squared dx. And of course, if you want to, you can just put, negative dx over x squared. You're going to be plugging numbers in anyway, right? And so if I want to determine how much the output has changed when I go from 1/2, 0.5, meaning 0.5, to 0.6, then I simply have to say, okay, well, dy is equal to negative 1/10, right? Because that was my dx, and I like using fractions because, they're easier, over 1/4, and negative 1/10 over 1/4 is going to be negative 4/10 or negative 2/5, and basically that is your dy, okay? Now, of course, you can, unnegativize it because we are dealing with distance here. And it really depends actually upon how the question is asked, but you get what I'm saying. Okay, so the question is, how does this relate to the actual change? Okay, well, the actual change, so delta y, would simply be the function at 0.6, so 1 over 0.6 minus 1 over 0.5. And that should be, relatively easy. That's 1 over 3/5 over 1 over 2/5, so 5/3 minus 5/2. So 5/3 minus 5/2. And I'm left with, the actual is negative, is that negative 5/6? Maybe I did a keystroke error right in here. So 1 over 0.6 minus 1 over 0.5. There we go. That wasn't exactly right. So this is negative 0.4, and this is negative 0.3 repeated, so that's negative 1/3. But if you compare those two, it's not a bad approximation, right? Not terrible. Okay, let's go ahead and let's move on to yet another one. Actually, before we do, let's go ahead and take a look at another one of those graphs, okay? And what that's saying right here is that as we go from 0.5 to 0.6, you notice that the curve right here, this is of course y is equal to 1 over x. This straight line right here is of course the tangent line, which actually works out to y is equal to negative 4x plus 4, which of course is the slope-intercept form of that point slope line right there. But you notice that as we moved from 0.5, right? As we moved from 0.5 to 0.6, there's your dx from 0.5 to 0.6. Obviously, there was a change, right? There was a change in y. Now that change in y right here is the actual change in y because this point right here is on the curve. This is delta y. What you were doing was you were actually finding dy, which was the approximate distance that it traveled vertically, the approximate change in output, because you were looking at the difference between this output and the output from the approximation point on the equation of the tangent line. So I hope this is sort of starting to make a little bit of sense as we keep moving forward. Now, of course, this can be used to deal with issues in terms of like real-world application and stuff like that. So of course you're going into an occasional word problem, and you're just going to have to mine it for the information that you need. Now, a spherical bearing has a radius of 3 centimeters when it is new. Use differentials to approximate the volume. Okay, the moment that it's spherical and its volume, its V is equal to 4/3 pi r cubed, right? Now, it says approximate the volume of the metal lost. So basically what you're looking for is the difference between the original volume and the volume when it wears down to a radius of 2.95 centimeters, okay? Now that means that my dr, the change in radius, is going to be 0.05. Well, let's go ahead and keep it with the negative, simply because it does decrease, right? Now we happen to know that dr, if I differentiate this, dv over dr is going to be 4 pi r squared, and my dv is going to be 4 pi r squared dr. Now, which r? Well, the original r, 3, right? And so your approximate change in volume is 4 pi 3 centimeters squared times negative 0.05 centimeters. Now 0.05 is 1/20th. So 4 times 1/20th is going to be 4/20ths or 1/5. So what you're going to get here is negative 9 pi over 5 centimeters cubed. And that is going to be the approximate change in volume. That approximates to negative 5.655. Now, if you wanted to actually compare it to the original, you would simply need the volume when it's at 3 centimeters and the volume when it's at 2.95 centimeters. So the delta V is going to be 4/3 pi 3 cubed minus 4/3 pi 2.95 cubed. Now, this right here is approximately 113.097. This right here is approximately 107.536. When you actually do the subtraction, you're going to get 5.561. Now, the actual change in volume when the radius decreases by 0.05 centimeters is this, okay? Now, obviously it decreases, so you plop a negative in there. I guess you could do that. But basically, I'm really more interested in whether you can get the absolute value correct. I'm really not interested in I'm really not interested in the sign, because when you actually write it out and explain it, if I ask you to explain it like answer in sentence form, you would just say, well, the volume decreases, and the decreases would take care of that negative right there. So I'm less interested in the positives and negatives in this than I was in the related rate problems. So let's go ahead and move on to the last problem that we're going to do. Okay, and this one says the radius r of a circle increases from a is equal to 10 meters to 10.1 meters. Use dA to estimate the increase in the circle's area. And of course, area, pi r squared. So dA dr is equal to 2 pi r, or dA is equal to 2 pi r dr. Now it's in the form of differentials. I'm going to plug in just like I did in the last one. And of course, in for this value right here, I'm going to plug my original r, which was 10 meters. And in for here, I'm going to put in how much it changed. So 0.1 meters. And so my dA is going to be 2 pi times 10 meters times 1/10 of a meter, and thankfully those kind of cancel out. So you get 2 pi meters squared, and 2 pi approximates to 6.283. Now, if you're looking for the actual, right, if you're looking for the delta A, you know that it's going to be pi times 10 squared, because 10 is where it started, minus pi times 10.1 squared, because that's where it wound up. And basically what you get here, actually it should be the opposite, so that right there. And so it's 6.315, and that as an actual is still pretty close to that as an approximation for how much the area has increased with a slight increase in the radius. I am sorry for not being able to be there today. I hope that these videos were helpful. Continue on to the older video that is last in the playlist, and I will answer any questions that need to be answered when I get back to class. But I hope you all are doing wonderfully, and I will see you soon. Bye-bye.